Okay, welcome everybody to the last webinar of the year. This is for electrostatics and circuits, Unit 10. And what I'm going to do is I'm going to start with the quiz that you took in class last Friday or today. I'm going to go ahead and mute my computer so I don't get any more dings coming in to distract me. All right, so what we have here is a very simple series circuit. The first thing that you want to do with any circuit problem is to find, that's not what I want, is to find the equivalent resistance of the circuit. So what I call, whoa, that's really bad. How did that happen? It's because I zoomed in, that's why. Okay, so the first thing that I want to do is find the REQ. That is not what I want either. Let's see. The REQ, there we go. For a series circuit is simply equal to, so for a series circuit is equal to the resistance of R1 plus the resistance of R2. You can think of it as the total resistance. So in this case I just have two resistors in series, so if I were to simplify this, it would be like having one resistor with the battery. And because they're in series, I simply add them together. So the 4 plus the 6 is my equivalent resistance, so my equivalent resistance is equal to 10. So if I were to replace these two resistors here with one resistor, it would have a resistance of 10 ohms. Now there's not a column in this table here for equivalent resistance, but if you wanted to, you can make your own little total row down there and put 10 ohms for the total resistance. The next thing that you want to do, so step one, is to find equivalent resistance. That's usually going to be the very first thing you do for almost every circuit problem if math is involved. Step two is to find current coming from battery. I also think of this as the total current. So total available current in my circuit. It may not always be the current going through every single resistor, but it is the current coming out of my battery here. So what we're going to find is this I value coming out of the battery. Since the total resistance is 10, so current is equal to voltage divided by resistance, and the total voltage is 20, and the total resistance is 10, I get a value of 2 amps for my current. Amps or amperes is what current is measured in. This is really just joules, sorry, not joules, coulombs, excuse me. This is coulombs per second. So amps is coulombs per second. If I could be in that magic school bus and go inside the wire and see how fast the charges are moving past me, that's what amps are. So the current of the circuit is 2 amps. The total voltage of the circuit is 20 volts. And I can go ahead and find the power of the circuit as well. Power is equal to current times voltage. So the total current is 2 amps and the voltage is 20 volts, so the total power should be 40 watts. Now when I go into the actual circuit, I have to figure out what's the voltage drop across each resistor, what's the current going through each resistor, what's the power being dissipated by each resistor. So we have to remember one of the rules. And the rule for a series circuit, remember this is a series, and for a series circuit, if I were to measure current, the current is the same throughout. The current is the same throughout the circuit. So if I measured an I value coming off the battery equal to 2 amps, then if I measured with an ammeter here, it would also be 2 amps. And if I measured with an ammeter here, it would also be 2 amps. Even inside the resistors, it is 2 amps. You can think of a series circuit as, one pathway, one pipeline carrying the water, one river. It's going to have one current. So the current is going to be 2 amps going through that resistor, and also 2 amps going through that resistor. Now if I wanted to find the voltage drop across each of my resistors, what is the voltage drop from here to here? Now the voltage drop is going to be the electrical potential difference. Electrical potential difference. And the electrical potential difference really is just voltage. I could have an electrical potential here, and I could have an electrical potential here. It'll always be less after the resistor, but the difference is what we tend to usually care about and what we can actually measure. So the voltage drop is going to be the difference in potential on each side of the resistor. And to find that, we use our other equation, V equals IR. Well, actually, it's the same as that equation there, it's just rearranged. And the current going through that resistor, we already said, is 2 amps. And that resistor has a resistance of 4 ohms. So 2 times 4 is equal to 8 volts. So the voltage drop across this resistor is 8 volts. I'm going to do the same thing for the next resistor, which is 6 ohms times 2 amps is going to give me 12 volts. Now we can see that the 8 plus the 12 equals 20, so I can check that off. All my math works out there. Power, again, is just current times voltage. So current is 2, voltage is 8. That's going to give me 16 watts. And then 2 times 12 is 24 watts. And again, 24 plus 16 is equal to 40. So that checks out there. We can see if we were asked about brightness, which bulb would be the brighter bulb if these were bulbs. It would be the one with the highest amount of power. So that one right there, the 24 watts, would be the brightest. No matter how the circuit is wired, if you figure out the power correctly, the highest power will be your brightest bulb. All right, that is a simple series circuit on your quiz. I'm going to go over a simple parallel circuit and then a combination circuit, and then I'll open it up for questions for you guys. All right, let me go. Let me go get this. All right, here's my simple parallel circuit. In the parallel circuit, I can see that my total voltage is 6 volts. So I'm going to put 6 volts down here for my total. And the first thing I want to do, as I said a while ago, is to find the equivalent resistance. In parallel, the equivalent resistance, 1 over the equivalent resistance, is equal to 1 over each of the resistors, or the inverse, the sum of the inverses of each of the resistors. So 1 over 6 plus 1 over 3 plus 1 over 2. And in the end, I want to take the inverse of that so I can find Req. And when I do that, I get a resistance of, for my equivalent resistance, what does that come out to be? One comes out to be 1. Comes out to be 1 ohm. So my equivalent resistance, or my total resistance, is 1 ohm. So now I can find my total current. So there's step 1, find equivalent resistance. Step 2 is to find the total current coming off the battery, which is equal to voltage divided by resistance. Always these two steps when you're doing math, guys. Equivalent resistance first, and then find the current coming off of the battery. So what I want to find is that current value there coming off of the battery. The battery voltage is 6 volts. The total equivalent resistance is 1 ohm. So I'm going to get a current of 6 amps, a total current of 6 amps. Now this is a parallel circuit, so I cannot just write 666 all along this column here. But what I can do is remember that for every loop, this is Kirchhoff's loop rule, which is conservation of energy. It says that for every voltage rise, the sum of my voltage rises have to equal the sum of my voltage drops. So if the rise is 6 volts here, the drop across the 2 ohm resistor has to be 6 volts. And in this loop here, I have another loop where there's only one resistor, so the drop has to be the complete 6 volts because the voltage rise plus the voltage drop must equal 0. And in the third loop, the electron could take this outer path here, again without going through any one of those resistors. It has to, the voltage rises by 6 in the battery and it would have to drop by 6 across there. This is called the loop rule. It is Kirchhoff's loop rule, and it is conservation of energy. Remember, voltage has to do with the volts is really just joules per coulomb. It's the amount of energy that each one of the charges has. So if you think about the charge getting energy as it goes through the battery, and then it's going to dissipate that energy as it goes through the resistor. We're going to lose energy. We don't lose charge. All the electrons do make it back to the battery, but the energy that the charge has is lost. So now that we've filled all of these in with 6 volts, we can just use again, current equals voltage divided by resistance to find the current in each one of the branches. Now these 3 branches will not have the same amount of current because the current is split. If you remember Kirchhoff's junction rule, says that the sum of the current going in must equal the sum of the current going out. So in this case, if I labeled this I1 and this branch I2 and this branch I3 and this branch I4, I would have to say that I1 is equal to I2 plus I3 plus I4. So what I'm saying is that the sum of these 3 currents here have to equal 6, and they're going to be proportionally distributed amongst these 3. Now the one that's going to get the highest amount of current is going to be the lowest resistor, because the current's always going to want to take the path of least resistance. So I know that the 2 ohm resistor is going to have the highest current. Let's see if that checks out up here. Voltage is 6, so for the 2 ohm resistor it's going to be 6 divided by 2, which comes out to be 3. And for the 3 ohm resistor it's going to be 6 divided by 3, which comes out to be 2. And for the 6 ohm resistor the current will come out to be 1. 1 plus 2 is 3, 3 plus 3 is 6. So that checks out. The sum of all the currents do equal 6. Now we need to figure out our power, which is just current times voltage. P equals IV. So the current is 1 times 6. 6 times 2 is 12. 6 times 3 is 18. Pretty straightforward, and I'm pretty sure that most of you got this correct on the quiz, but I did see a couple of groups struggling with where to start. That's why I want you to remember step 1 is to find REQ, step 2 is to find the total current, and then work your way from there based on what type of circuit that you have. All right, that is a simple parallel circuit. Now let's get the more complicated one. I saw most every group having trouble with this one here. So we definitely want to go over this combination circuit. All right, let me go ahead and delete that. paste in my combination circuit. All right, so for the combination circuit, let me just warn you that I will not just blanketly fill in any column and make everything the same. It's a combination. So you're not going to have the same current in every resistor. You're not going to have the same voltage drop across every resistor. That is my big red flag. Do not do that. Again, the first step is going to be to find the equivalent resistance of the circuit. So because it's a combination circuit, what I want to do is I'm going to find 2 or 3 of the resistors that I can find the equivalent resistance for. I can look at this and easily see those 2 are in parallel with each other, and they're in parallel with each other, nothing else. So what I'm going to do is I'm going to redraw the circuit like this. And this is going to stay 1 ohm. And now I'm going to say, if I were to combine those 2 resistors into one resistor, what would the equivalent resistance be for that resistor? And so I'm going to use my parallel rule for equivalent resistance, and that's going to be 1/8 plus 1/8, and then take the inverse of that. That comes out to be 4. So REQ is equal to that, which comes out to be 4 ohms plus that resistor there. Now remember, that resistor is in series with the 4 ohm resistor. They're in series with each other, and when they're in series, I just add them together. So my total equivalent resistance of the circuit, if I were to combine these 2 into one, like that right there, that resistance would be 5 ohms. So the equivalent resistance of the whole circuit is 5 ohms. I need to grab my charger real quick. Okay, we have power. All right, so the total equivalent resistance of the circuit is 5 ohms. So if I wanted to put that in my table, I could put it under here, right there. The total voltage is given to me. That would be this number right here. That still stays 15 volts. Cannot get any more voltage than what my power source provides me. So now that I have total resistance and total voltage, step 2 would be to find the current of the entire circuit, which is going to be voltage divided by resistance. My total voltage is 15 volts. It's given in the diagram. And this R is the one that I just found, the equivalent resistance, or you can think of it as the total resistance of the circuit. That's going to be 5 ohms. So the 15 volts divided by the 5 ohms gives us a current of 3 amps. Now, what I saw some groups do is they found the 3 amps, but then they went through and they wrote 3, 3, 3 in each one of those. Now remember that the current coming off of this battery is 3 amps. So the current going through this equivalent resistor would be 3 amps. The current going through that equivalent resistance would be 3 amps. The current going through that resistor would be 3 amps. So the only one that I can write down 3 amps for is the 1 ohm resistor. That one is going to be 3 amps. Now that current is going to be split. If I go back to my original drawing, this would be I1, which is 3 amps, and that's going to be equal to the current going through that branch plus the current going through that branch. So I1 would have to be equal to I2 plus I3. In this case, they're both 8 ohm resistors. So that makes figuring out the current pretty easy. We just have to split it in half. But what if they weren't the same? How would I figure out what the current going through that resistor would be? Well, I would have to figure out what the voltage drop was. And to figure out the voltage drop, I would need to come back to this, this resistor here, or maybe figure out what the voltage is in this resistor. So let's go ahead and do that first. Let's just pretend that we don't know that that splits into 1.5 and 1.5, and I'll show you how to calculate it. We know that there's 3 amps of current running through this resistor, and we know that it's 1 ohm. So I can calculate the voltage drop. We'll do that in green. We're going to calculate the voltage drop from here to here. So the difference between electric potentials on each side. That's going to be 3 amps times 1 ohm. So the voltage drop here will be 3 volts. So I can go ahead and write that. For the 1 ohm resistor, the voltage drop is 3 volts. Now I know my total voltage is 15, and I know that the voltage has to be totally used up when it goes through the circuit. So if I subtract, if I have a rise of 15 and I have a drop of 3, and then I'm going to have another drop, and all of that must equal 0. So I can figure out that 15 minus 3 is 12, so my other drop must be 12 volts. So the voltage the voltage drop, or the potential difference across this resistor, would be 12 volts. Now, when I come back up here to this drawing, those two guys are in parallel. So guess what? The voltage drop here will be 12 volts, and the voltage drop here will be 12 volts. So now I can come put that in. 12 volts times 12 volts, and look there. I have only one unknown in my Ohm's law equation. Current is equal to voltage divided by resistance. So that's going to be 12 divided by 8. And 12 divided by 8 is indeed 1.5. And 12 divided by 8, we'll do that again, is 1.5. Those definitely add to 3, so we are good there. Remember, our total current was 3. Now for power, that's the easy one. That's just current times voltage. So when I multiply, P equals IV, when I multiply current times voltage, 12 times 1.5 gives me 18 watts. And I'll get 18 watts again there. And I'll get 9 watts there. And my total power, let's see, that would be 45 watts. If I asked you which bulb was the brightest, it would actually be the two that are in the parallel branch. And some of you may be going, hey, in our labs, the one that was kind of in series by itself with the battery was always the brightest. That is true, but in the labs that we did, the bulbs always had the same resistances, and that's why that happened. What I want you to realize is that brightness is a combination of current and voltage. So here, these guys have the lowest current and the highest voltage, and this one has the highest current and the lowest voltage. So it's not current, it's not voltage that determines power, brightness, it's the power that determines the brightest. So the 18 watt resistors would be the brightest if we were talking about light bulbs. If they don't give you a resistor value or the resistance value of the light bulbs, or even if they don't give you the voltage, if they just say you have, let's say they told you had 3 light bulbs with the same resistance each, wired this way in a circuit, which one would be the brightest? Well, if you wanted to double check yourself, you could make up a value for resistance. You could just say they're all 1 ohm each and find equivalent resistance. And if they didn't tell you the battery value or the voltage source, you could make that up too. You could make that 1. If they don't tell you, as long as they say they're all the same, the resistances are all the same, you could figure out which one is the brightest for a 5-volt circuit, for a 6-volt circuit, for a 20-volt circuit. It really doesn't matter what the voltage is, as long as you understand the resistors are all the same value. That's if they don't tell you and they ask you to find brightness. You still can quantitatively find that just by using your own numbers. Just FYI. Okay, so that is the combination circuit. Now notice here that my total current was 3, and I have a 3 there, and a 1.5 and a 1.5. I have a total of 15 volts, a 12, a 12, and a 3. So they don't all add up to be 15, right? The ones that are in parallel with the series add up to be 15. And these two that are in parallel add up to the total current. So just be leery of those combination circuits. You can't just make blanket statements. You've really got to break them down, simplify them down to figure out what the equivalent resistance is and the current is, and then work your way back up. Okay? I hope that helps with simple series, parallel, and combination circuits. Sophia wanted to go over number 5 on the circuits worksheet. So I'm going to find that one real quick. Sophia, at the top, it just has the number 1 on that page is just asking you to find the equivalent resistance of the two 8 and 6 ohm resistors. Is that correct? Just want to make sure we're working on the same page. Okay. So we want to do number 5 on that one. Let's see if I can get open. See if I can open up real quick that document and paste that over. So electrostatic circuits test review. It's going to be in here for us. No, it's not in here, is it? Okay, I'm just going to have to draw it. Yes, it is on the review. Okay, I'll draw it real quick. It looks like we have, I'm going to change back to black. Looks like we have a battery, and then it splits into a parallel branch with R1 and R2 in series with each other. Then we have R3, it's in parallel with R1 and R2. Then we have these, and then we have that guy there. So what do they tell us? They tell us that the current from the source is 2 amps. So I know that the current running through here is 2 amps. They tell us that R3 current is 1.5. Let me go ahead and label those. R1, R2, R3, R4 and R5, and then R6. So you won't have anything that complicated in the main part of the test like this, but there is going to be a bonus circuit that would be a more complicated one like this. So do you guys still want me to go over this one? Yes, okay, I thought so. I'm going to just fill in what we know here. I know that, say, the current in R3 is 1.5 amps. And just by looking right now, if I know that the current coming in is 2 amps and the current here is 1.5 amp, then what does the current have to be in this branch here? The 2 must be equal to 1.5 plus the current going through this branch here. So I know this current must be 0.5 amps. So you can go ahead and fill that in on your chart. The current through R2 must also be 0.5 amps because it is in series with R1 and R2. So in this branch, the current is 0.5. In this branch, the current is 1.5. They would recombine here to have a current again of 2 amps, and then that current is going to split between these guys. Did they tell us the resistance of R4 and R5? No, they did not. they told us that R4 has a voltage drop of 4 volts from there to there. And they told us the current, look at that, they did tell us the current going through R5 is 1 amp. So this 2 amps coming in splits into 1 and it only splits one other way, so I know that the current over here is also 1 amp. So as we're figuring these things out, you can fill in the blanks in your table. Then the current recombines here to be 2 amps again. And the current through I6 is going to be 2 amps as well, because there's no split here, so it has to be 2 amps. So there's a few things that we can figure out. We know the resistance of R1 is 5. R1 equals 5 ohms. R2, they tell us, is a 3.5 voltage drop. So from here to here is 3.5 voltage drop. R3 is 1.5 amps, we already know that. R4 is 4 volts. 1 amp. R6 is 2 ohms. Oops, let's do that in blue. They told us that R6 is equal to 2 ohms. Okay, so anywhere along here, if I know 2 out of the 3 variables in V equals IR in Ohm's law, I can figure out the third. So right away, right here, I can see that I know that R1 is 5 ohms, and I know that the current is 0.5. So I can calculate the voltage drop across R1. So the voltage drop across R1 is going to be 2.5 volts. So I'm going to go ahead and write that in on my diagram since I don't have the chart. So 2.5 volts there. Let's look at R2. We know the voltage drop for R2 is 3.5 volts, and we know the current is 0.5 amps, but we don't know the resistance. So to get the resistance, I would just need to say 3.5 divided by 0.5 equals my resistance for R2, and that's going to be 7 ohms. So resistance of R2 equals 7 ohms. Well, now I can do something kind of nice here. These two are in series with each other, so I can add their voltages together to get a total voltage in this branch, a total voltage drop from here to here to be, let's see, 3.5 plus 2.5 is 6 volts. So if the voltage drop from here to here is 6 volts, then guess what the voltage drop is from here to here? You got it. It is 6 volts. So the voltage drop across R3 is 6 volts. Aha! Now we have current for R3 and we have voltage for R3. So guess what we can find? Resistance. And resistance is just going to be the voltage divided by the current. So that's going to be 6 divided by 1.5. And for R3, 6 divided by 1.5 comes out to be 4 ohms. So R3 equals 4 ohms. So at the beginning of the unit, when I said it's kind of like a puzzle, this is a perfect example of this huge puzzle, right? We have a lot of different working parts here. All of them are based on the principle of V equals IR, that voltage is additive in series, it's the same in parallel, current's the same in series and additive in parallel. All of those principles come together, all of those rules come together to put together the pieces of the puzzle. What's next? Oh, Trevor says that I equals V over R is the superior way to write Ohm's law. It is the way that it is written on your formula chart, but you know, old habits stay strong, and this is the way that I learned it way back when in high school and college, so it's just what's stuck in my brain. If you remember that I equals V over R, that's all good and well, works all the same. What do we have left to fill in? Now let's work on this branch here. We know the voltage drop is 4 volts. We know that the current running through here is 1 amp. So I can figure out what the resistance is. Again, the resistance is just going to be the voltage divided by the current, just like we did up here. So 4 divided by 1 is going to give me a voltage drop of 4 volts. Oh wait, sorry. We knew the voltage drop was 4 volts. We're trying to find the resistance. It's going to give me a resistance equal to 4 ohms. So that's going to be a 4 ohm resistor there. And then on the opposite side, if I know that the voltage drop across R4 is 4 volts, then I also know that the voltage drop across R5 is 4 volts. So voltage equals 4 volts because they're in parallel with each other and only each other. There's not two resistors here like there were up top. So up top they had to add together to equal the total voltage of the other side, but here they're just in parallel with each other, so the voltage drop has to be the same. And now that I know the voltage drop to be 4 volts and the current to be 1 amp, I can find the resistance by taking voltage divided by current. And the voltage is 4, the current is 1, so the resistance of R5 actually comes out to be 4 ohms as well. All right, we're on the home stretch here. R6 is going to be 2 ohms and 2 amps. So all we need to do is V equals IR. 2 amps times 2 ohms gives me a voltage drop of 4 volts. All right, now we figured out everything for each individual resistor, but what is my total voltage from the power source? What is my total voltage of the power source? Well, I'm going to go through and I'm going to combine these two, or I'm going to combine the branches. Really, it's like I have a voltage drop of 6 volts there, 4 volts here, and what do we say here? 4 volts here. So 6 plus 4 plus 4 gives me a total voltage of 14 volts. And they told me that my total current was 2 amps. So if I want to find the total resistance, I could find the REQ of everything, or I could just use my Ohm's law equation and say that the voltage divided by the current is equal to the resistance. So 14 volts divided by 2 amps gives me 7 ohms. And that is question number 5. So if you needed help with combo circuits, this is a really good one to dive in and see if you can put it all together, because it really is a complicated one. The ones on a multiple choice section or maybe an FRQ on the test won't be quite this complicated, but like I said, there is going to be a bonus question at the end of the multiple choice where I give you the table and I tell you a few things and you've got to figure everything else out in the table. You're very welcome, Sophia. All right, Mia says, if you can get to it, could you explain the thought process behind figuring out FRQ number 2 on the test review? It's not urgent or anything, but it would be great if you could explain. Number 2, FRQ number 2 on the test review. Let me pull that one up. I tried to give you guys, like I said in class, as much practice as possible. So there's lots of work here. The thought process of number 2 . So this was the experimental design question. You needed to state the measurements you would make and how you would use the equipment to make them, include a neat labeled diagram of your setup. So the question was, in 1 second, do fewer electrons leave the bulb than enter the bulb? So what you would need to do there, if you wanted to figure out the number of electrons that enter the bulb and leave the bulb, you'd need to measure the current on both sides of a bulb, and what you would see is actually the current on either side of the bulb is the same. So let me go ahead and write a few things. So to test statement 1, I would put a light bulb in my circuit, and then I would come back and say, well, I'm going to put an ammeter after the bulb, and I'm going to put an ammeter before the bulb. And if those current readings are the same, let's say this is equal to 1.0 amps, and then I come over here and see, oh, that's equal to 1.0 amps, then I could conclude that the number of electrons entering the bulb and leaving the bulb have to be the same. The second statement says, does the electrical potential energy of the electrons change while inside the bulb? So what I would want to do to test that is I would actually put in a voltmeter, and I would put a voltmeter in parallel with that light bulb. So I put my voltmeter in parallel with my light bulb, and what a voltmeter does is it measures the electrical potential difference. Electrical potential difference. Now, as I was telling a student today, that keyword difference is actually a big deal. Electric potential is talking about volts, and volts is the amount of energy per charge. So if I could get into my little magic school bus and watch the electrons fly by me in the wire, and I could measure how many joules of energy there was per coulomb of charge, that would be what the voltage is. And that would be electric potential. So that would be joules per coulomb. That's what volts is, joules per coulomb, or energy per charge. Now, the amount of energy per charge that the electrons, or that the charges have here at this point in the circuit, will be different than the electric potential that the electrons have here in the circuit. Okay? And if this was a 12-volt battery, like what's found in your car, then the electric potential on this side would be 12. The electric potential on this side would have to be 0. So is there more? So what this is saying is that there would be 12 joules per 1 coulomb of charge. What this side is saying is that there would be 0 joules per 1 coulomb of charge. So does the amount of energy that the electrons have change while it's inside this light bulb? And the answer is absolutely yes. And the reason is because I can measure the electrical potential difference, which is the voltage. Now, by adding the word difference on there, that's when we talk about voltage. That's what voltage is. Electrical potential is measured in volts, but the electrical potential difference is the voltage. I know it sounds like a little, not that big of a deal, but electrical potential difference is what we can measure. Now, does it mean that this is 12 volts and that's actually 0 volts? No. This could have been, let's see, this could have been 36 volts. And if this side was 36 volts of electric potential, how much would the other side have of electric potential? Well, what is 36 minus 12? It's 24. Whoa, that does not say 24. The difference between the 36 and the 24 is 12 volts. So what you need to see is that when we follow conventional current flow, if this is the positive side of the battery, and this will be on your test tomorrow, so pay attention. The positive side of the battery is here, the negative side of the battery is here. The electric potential before the resistor will be higher than the electric potential after the resistor. Because what does the resistor do? The resistor slows down the electrons, but it also removes energy from those electrons, removes energy from electrons. How do we know there's energy removed? Well, I can feel it. What can I feel it as? I can feel it as heat. I can see it a lot of times. If it's a light bulb, what can I see it as? I can see it as light. So that energy from the little electrons moving through the wire, they had energy, but then that energy was given off as heat and light. Kind of like a combustion reaction. But were the electrons given off? No. The number of electrons coming into and leaving were the same. So that's why the junction rule is conservation of charge, and it deals with current. And the loop rule is conservation of energy, and it deals with the voltage. Okay? So that is a quick rundown of number 2 on the FRQ. And then it goes into the whole idea of the bulb being ohmic or non-ohmic, and we talked about that part in class. And the rest of that answer is on the key. But I think what we talked about is definitely valuable and worth going over. All right, I'll open it back up to questions to you guys. If you don't have any more questions, then I'll continue talking about the quiz that you took in class. Okay, another concept that we went over and tested you on the quiz is what affects the resistance of a wire? And the equation is rho times L over A, where rho is not density this time, it is resistivity. And this is dependent upon the material. So it's going to be a constant for different materials. So, for example, silver is going to have a lower resistivity value than, let's say, aluminum. So it's going to have a lower resistance. I would rather use silver wires in my wiring in my house than aluminum wires for a number of different reasons, but more specific because the resistance of those wires would be less. L is the length of the wire. So if I have a long wire versus a short wire, the one that is longer is going to have more resistance. Okay? And then the A stands for area. It is the cross-sectional area. Now what does that mean? Now imagine this was a rounded pipe. I'm not good at drawing 3D drawings, but imagine that was a rounded pipe and I were to cut it into 2 pieces. And then I were to look at one of the ends. Well, if it was a round pipe, that end would look like a circle. The area of that circle would be the cross-sectional area. And the area of the circle is pi r squared. So you can substitute in pi r squared for that area there. So we can further see that resistance is equal to rho for the material times the length of the wire divided by pi r squared. On the quiz, there were 4 different pipe lengths and diameters. So the first one it was long and wide. The length was equal to 8. The diameter was equal to 2. And the next one was not wide and short. Length was equal to 4, diameter equal to 1. And the next one was long and skinny. Length equal to 8, diameter equal to 1. And the last one was short and wide. Length equal to 4, diameter equal to 2. So, which one is going to be the least resistive? Which one is going to be the most resistive? Least resistive. So the shorter I am, and the fatter, the wider it is, the less resistant it is. So here's my two short ones, here and here. The wider one's going to be the least resistive. So this is going to be, if this is A, B, C, D, and I rank them, D is going to be the least. Which one is going to be the most? Well, the skinniest, longest one is going to be the most. So we can quickly see that C is going to be the greatest resistance. And then if I have B and A, which are left, one is long and wide, and then one is short and thin. What matters more, being thin or being short? And what I'm going to tell you is that being thin matters more because of that squared value on there. Being thin matters more because the squared value on there. So B is going to be the next greatest resistor because it is skinny, and then A is going to be the next because it is wide. Remember, it is long, but being long doesn't count for as much as being skinny does. That's just looking at it conceptually without really doing any math. You can go in there and use these numbers to figure out what the R would be equal to. And remember that the rho doesn't change because they're all the same metal. Pi is not going to change because it's a constant. So what we really get is that R is proportional to L over little r squared. So you can just take the 8 and divide that by 2 squared, which is going to be, that's 8 divided by 4 is going to be 2. And then you can take 4 divided by 1 squared, which is going to be 4. And then 8 divided by 1 squared, which is going to be 8. And then 4 divided by 2 squared, which would be 1. And then I could see that C is the greatest, B is the next greatest, A is the next greatest, and D is the least. And I have a lot of people asking me, well, but that's D, that's not R. Well, let me ask you this. If D is decreased by half, what does R decrease by? Well, R for this would be 1, and R for this would be 0.5. So what did R decrease by? It decreased by a factor of a half as well. So it really doesn't matter. Alrighty. That is number 4 on the quiz. Number 5 on the quiz is just talking about equivalent resistance. And so we have several resistors in here, and we're asking which one is the most resistance, which one is the least resistance, etc. Most of you should know by now that if I have 2 resistors in series, that is definitely going to be more than 2 resistors in parallel. All of these are going to be 6 ohm resistors. And so the equivalent resistance between these, we just add them together, we get 12 ohms. The equivalent resistance between these, they are in parallel. Now remember, this is just a segment of the circuit, and we can clearly see that, looky here, I have a current coming in, and that current would have to choose a path that way or that way. This is a parallel. These resistors are wired in parallel. So I'm going to say that the equivalent resistance is equal to 1 over 6 plus 1 over 6. And when we take the inverse of that, it'd be 2/6, which is 6 divided by 2. So that comes out to be 3 ohms. So wiring resistors in parallel versus series, the exact same resistors, the equivalent resistance is going to be way less if they're wired in parallel. What happens if I add a third resistor to that? So now I have the same two 6 ohm resistors, but I'm going to add a third resistor to that branch. 6 ohms, 6 ohms, and 6 ohms. And what I've said in class over and over again is that the more parallel paths that we add, the less the overall resistance is going to be. And I gave an analogy of going to the water park. And you climb up that slide, and there's one path to go down versus two slides to go down versus 3 slides to go down. How many people can we get through? Which one's going to be the winner? This one's going to be the winner. I can get more people down the 3 slides than I can just the 1 or the 2 slides. So the overall resistance goes down, and in this case, the equivalent resistance came out to be 2 ohms. How do we get that? 1/6 plus 1/6 plus 1/6, that's 3/6. And then I inverse 3/6 to be 6 over 3, and that equals 2. The last one, or the last two, were combination. So we had that and that. And again, they're all 6. So now I have to combine, I have to simplify. So I'm going to combine the two that are the easiest. Well, these two are in series with each other because they're in the same branch. So these two are in series. So I just add them. So that side is 12 ohms. I can simplify that down to something that looks like this. 12 ohms, 6 ohms. Now those two are in parallel with each other. So I'm going to add 1/6 plus 1/12. And then that comes out to be, what would that be, 2/12? 3/12, 12 divided by 3 is 4. So I was just getting a common denominator there. If I multiply the 6 times 2 to get 12, I had to multiply the 1 times 2 to get 12. 2 plus 1 is 3. Common denominator stays the same. 3/12. Invert that would be 12/3. That comes out to be 4. So the equivalent resistance of this guy is 4 ohms. So a little bit more than that one there, because I have a little bit of series in there. And then the last one in this example, I'm going to draw it sideways so I can fit it on the same page, was a series in series with 2 parallels. And this was 6, this was 6, this was 6. Now which two can I combine first? I can combine these two that are in parallel and convert it to something like looks like that. The first one would remain 6. Now these two are going to combine into basically what this was right here, and that had an equivalent resistance of 3. So I don't even have to do that math again. Now those are in series, so I just add them together, so that comes out to be 9 ohms. And that's how we find equivalent resistance. Other questions? All right, on the bonus question. Okay, Trevor has one real question. What would the circuit diagram look like for FRQ number 1? The 3 wires entering a bulb is somewhat confusing. Let me look it out. FRQ number 1. Okay, so the circuit diagram for number 1 on the FRQ. That's a great question. So what they drew for you was a rendering, a drawing, right? And the drawing looks something like this. There's a battery, positive terminal, and they had a light bulb here, and then they had from there going to another light bulb, going to another light bulb, and then they had this one connected to that one, and then they had this one connected to that one. And they labeled them A, B, D, C. So actually this one they had the wire coming around here like that. Let me fix that just a second. Whoops, that's not what I wanted. I just want to make sure I draw it like they did. Okay, so there's my C, and they show C being connected there, and we'll say that that is connected there, and then that one is connected there, like that. The circuit diagram for this one would of course have the battery looking like that, and then you're going to have A in series with the battery. You can see that there's a straight path there with the battery, and then you're going to have a split at this point right here. The current can go this way or this way. So I'm going to draw that like that. And then B is directly connected to C. And then the current rejoins after C. The current splits from B and then goes over to D, and then it rejoins after C. So A, B, C, D. And if you were asked, which in this question you are, to rank the brightness of the bulbs, they all have the same ohms of resistance. So A would be the brightest because it's getting the full current of the battery. Remember, the current goes around this way. But if I put an ammeter here or here, it's going to be the same. So A is getting the total current. The current between this branch and this branch is being split. But D, or these two parallel branches, will have the same total voltage drop. So the voltage drop from here to here will be the same as from here to here. So since there's only one resistor to get all of that voltage drop, I know that it's going to be the next brightest. And then the B and C will be equally bright but less dim than the D because they have to share the voltage in that parallel branch. But that is what the circuit diagram looks like. Awesome. I'll go back to the quiz. Again, if you guys have, okay, Mia says she has a question. Conceptually, I still would like to look at number 11 on the practice test to let it sink in despite already seeing the periscope. Number 11 on the practice test. Is this the one about the identical light bulbs can be attached to identical ideal batteries in 3 different ways, as shown in the figure? The ranking from the lowest to brightest, the total power produced by the battery is? Okay, so with questions like this, Mia, like I said before, if you want to see, they're asking about total power, and you know power is current times voltage. All of those batteries are identical. So I have a battery here, and that battery is connected to one light bulb, and then the next one I have one battery connected to 2 light bulbs in series, and the third one I have a battery connected to 2 light bulbs in parallel. So the ranking from lowest to highest of the total power produced by the battery. From lowest to highest. Another way you could think of this is which bulbs are going to be the brightest. Well, the bulbs are going to be the brightest when they have the highest voltage and highest current, right? So our power equation is current times voltage. Since they said the batteries were identical, I can make up whatever numbers I want, so as long as they're the same. So I'm going to make my life easy and say that this battery is 1 volt. So each one of those batteries has to be 1 volt. I'm again going to make my life simple and say that this resistor is 1 ohm. 1 ohm, 1 ohm, 1 ohm, and 1 ohm. First step to any problem is to figure out the REQ. REQ here is going to be 1 ohm. REQ here is going to be 2 ohms, because I'm just adding them. REQ here is going to be 1 over 1 plus 1 over 1. That is 2 over 1. Take the inverse of that. We get 1 over 2, which is equal to 0.5. So we can see that we need to label these A, B, and C, right? So here is A, B, and C. Now I need to figure out the current. So if the total voltage is 1 volt for each of these, what is the total current running through this? Total current is V divided by R. So 1 divided by 1 is 1 amp. I is V divided by R, so 1 divided by 2 is 1/2 amps, or 0.5 amps. And the current here is 1 divided by 0.5, which would be 2 amps. So I have the most current running through my parallel one. That makes sense. I have the least amount of current running through the two that are in series with each other. Now I can figure out what the voltage drop is across each light bulb. The voltage drop across that light bulb, well, I know the current running through there is 1. So the voltage drop has to be equal to 1 volt, because voltage is current times resistance. Resistance is 1. Current is 1, so voltage has to be 1. Now let me figure out the power for that. Power is I times V. Again, power is going to be 1 watt for that bulb. Now, the voltage drop across, well, let me do it in green. The voltage drop across here and here is going to be 0.5 volts and 0.5 volts. And the current running through there is also 0.5 amps. Why was the voltage 0.5 here? Well, because the 1 volt had to be split evenly between the 1 and 1 ohm resistor. So what is 0.5 times 0.5? Power. 0.5 times 0.5 is 0.25 watts. So my total, and this one would be 0.25 watts. 0.25 plus 0.25 gives me a total power of 0.5 watts for B. And then for C, I know the voltage drop is going to be 1 volt across each one of these, and 1 volt across that one. And so my current is going to be evenly split. It was a total of 2 amps, so I know I'm going to have 1 amp here and 1 amp there. And so my power is going to be 1 times 1, which is 1 watt. And power here is going to be 1 times 1, which is 1 watt. Add those two powers together, and I get a total power of 2 watts. Okay, so you can definitively see with the math that B is going to be the least, and then A, and then C. Conceptually, if you want to think about it, A and C are really going to be the same thing. This bulb is going to have the same brightness as this bulb because they're both attached to a 1 volt source, and they're the same resistance, so they must have the same power output. But in this circuit, I have two of those with the same power output. Think about the vanity lights we did in class. Which one was the hardest to look at? The one that was all in parallel. It didn't matter how many parallel I had. Every time I added another one, if I had a 3 vanity bar light or a 5 vanity bar light, or light bar, sorry, it wouldn't matter how many lights I had in there, they would all be the same brightness. So that means I need that much more power to light that circuit. And of course, this one in series, the current's going to be split. I'm sorry, not the current. The voltage is going to be split. The overall resistance is going to be less, so the current is going to be really wimpy and weak in there. So even though you're adding these two powers together, there's less voltage, there's less current than either of these bulbs over here, so it's going to have the least amount of power. Okay? Did that help, Mia? Any other questions about number 11 on the practice test? Awesome. Okay. On the quiz, I want to go over number 6. It was the one with the batteries. It's it's similar to what we were just talking about, but it's something I didn't directly say in class, so I want to make sure we understand it. I'm just going to draw light bulbs because that's what's on there. So there's a light bulb with 1 battery. There's a light bulb with 2 batteries. There's a light bulb with 3 batteries. And then we have a light bulb with 2 batteries, but wired in parallel. 2 batteries, but they're wired in parallel. So what's going to happen if I have 2 batteries? What's going to happen if I have, let me draw it that way so it's less confusing. What happens with the batteries whenever they're in series with each other? You add their voltage. So if this one was 1 volt, then this one would be 2 volts, and this one would be 3 volts. And the more voltage that a light bulb gets, the brighter it's going to be. Now, let me redraw this one. If I have a light bulb with 2 batteries wired in parallel, well, this light bulb, 1 loop here, if that's a 1 volt battery, then there's a 1 volt rise, and there has to be a 1 volt drop across that bulb. Same thing here. There's a loop here, but a 1 volt rise is a 1 volt drop. So the only amount of drop I can have across that light bulb is 1 volt. Same here, only 1 volt. So what happens whenever we add batteries in series is that their voltages add. That makes sense. But whenever I add batteries in parallel, it doesn't increase the overall voltage. Actually, it doesn't change the overall voltage at all. It really just increases what we call the capacity, which is what the question you answered in your lab, between what's the difference between a AA versus a D battery. They're both 1.5 volts, but the D battery is much larger than the AA battery. Why is the D battery much larger than the AA battery? It's because there's more stuff in it, there's more chemicals. It can last longer. So why would I want to wire batteries in parallel? To make them last longer. Hannah says, what does a voltage drop mean? So a voltage drop, if you remember Kirchhoff's loop rule, says that the sum of the voltage rises, and anytime we go from a negative to a positive side on a battery, we're going to have a voltage rise. We're going to give that charge energy. So in this case, it would be plus 1 volts when I go from the negative to the positive side of the battery. Now when I go around the circuit, anytime I cross a resistor, that resistor is going to slow down the electrons And by slowing the electrons down, it's going to take energy away from them. So it's going to drop the voltage. And in this case, there's only one resistor there. So I know it's going to drop it 1 volt because the sum, that was really bad. The sum of the drops has to equal the sum of the rises. So the sum of the voltage rises must equal the sum of the voltage drops. So a resistor is going to take away energy. It's going to lower the amount of energy that a charge has. I like to think of this graph in my mind when I think about voltage rise and drop. So imagine that this is the baseline, 0, and the battery is going to bring the voltage up 6 volts. And if I had a resistor here, and a resistor here, and a resistor here, and let's just say they're all the same ohms, 2 ohms, 2 ohms, 2 ohms. So, and this is a 6-volt battery. Each one of these resistors is going to drop the voltage by the same amount. So I'm going to go through the wire, and then I'm going to go through the 2 ohm resistor, and I'm going to drop that voltage. So the voltage would drop from 6 to 4. But the difference is 2 volts. So we say that the voltage drop across this resistor, if measured, so the potential, electric potential would be 6 here, it would be 4 here, but the voltage, which is the difference, is 2 volts. And that's what we care about. We don't care that that's 6 and that's 4. What we care about is the difference. Now you do need to understand that after the resistor, when we're going from positive to negative, that the electric potential will always be less. And then we go through another wire, and then we go through another resistor, and we drop the voltage. How much do we drop the voltage by? Well, we're going to drop it another 2 volts because it's the same resistance. So we dropped it another 2 volts. So we went from 4, that's 6, that's 4, this would be 4, this would be 2, and then we go through this wire right here, and then so the potential here would be 2 volts, the potential here would be 0 volts. And so we end right back down here at 0. So the third voltage drop is another 2 volts. You'll never really see me talk about the 6, the 4, the 2, the 0. What we mostly talk about is the voltage, which is the electrical potential difference. But each time we add a resistor, there is more and more drop. Yes, Mia, the voltmeter measures the voltage drop. It measures, more technically, you could say the electrical potential, remember that word, difference. It measures the difference between these two electric potentials. The voltage drop is what you use in equations. Yes, Hannah. All we care about when we use Ohm's law and we're using V equals IR, what I care about is the voltage drop across that resistor. I'm never going to use that 6 or 4. I'm going to use the difference between those. So it's good to conceptually understand that that potential is 6 and that's 4, but what we're going to use in our equations is the 2 volts, which is equal to the current times the resistance. So I could figure out that the current here would then be 1 amp. Very good question, Hannah. All right, any other questions? Awesome, Hannah. I'm so glad you asked that because I'm sure there's a lot of other people with the same question. And you know, we go over graphs like this one in class and it stays on the screen for sometimes probably about 20 seconds. And so it's something that I feel like, oh, well, we've gone over that, but it, you know, you guys need to see it multiple times for that kind of stuff to really sink in. Trevor says, so if you put it before and after battery, it tells you the initial voltage given by the battery minus 0 because all voltage must be used up. So it gives just the total voltage of the battery. If I put it on the battery, if I put it on the terminals of the battery here, let's see, this is my voltmeter. then it's going to tell me the difference in potentials from that side to that side. And if it's a 6-volt battery, then again, this could be 12 and this could be 6. Or this could be 6 and that could be 0. This is typically how we think about it, but the actual metals that are used will determine what these potentials are. But what we care about is the difference, so we usually like to think of it as 6 and 0 versus 12 and 6. But yeah, whether you're using zinc and cadmium or lithium and carbon, whatever it is, you need to look at in AP Chem, you've got a list of reduction potentials, and those reduction potentials are what's going to determine the potential here and the potential here. And it's the difference between those reduction potentials that gives us the voltage of the battery. Okay, I think there's another great one to go over on the quiz, and this is a tricky one. It's not really tricky, but it's one that even sometimes my superstar students get wrong, just because we think we understand it and we can do it real quick, but then when we stop and look, we're like, oh, okay. So let's look at this. And the way it was pictured, the way the circuit diagram was drawn, makes it a little trickier as well. Okay, so this is a switch right here. There's my battery, and what do I have? I have these 3 resistors that are in series with each other, but they are in parallel with these 2 that are in series with each other. So these 2 are in series with each other, these 3 are in series with each other, but the 2 branches are parallel with each other. So I could redraw it like this, which maybe you're more comfortable with. Same thing. I don't think I have, Trevor. So it wants to know when the switch closes. Oh, I forgot to put my switch on my new drawing. So the switch is here. So when the switch closes, will the current in resistor A increase, decrease, or remain the same? So this one is resistor A, and that one would be here. Does the current in resistor A increase, decrease, or remain the same? Go ahead and text me your answers that you put on your quiz if you got to this question. So we're talking about current in A. Did it increase, decrease, or remain the same when the switch is closed? Any brave souls out there? Sophia says increase. Ethan says decrease. Trevor says increase. Mia says increase. I said when the switch closes. When the switch closes, what will happen? I love it. I love this question. This is why I love it, because the answers are all over the place and we have different justifications. So let's run through this. What does current depend on? Current depends on the voltage divided by the resistance. Now, all of these resistors have the same ohms. By closing the switch, will that change the resistance of resistor A? No, of course not, because that's determined by the material, the length, everything. Now let's look at the voltage. Since resistance isn't going to change, the current's going to depend on whatever the voltage does. If I follow the loop rule, They didn't tell me the voltage of the battery, but I could assume, let's say it's 6 volts. I have one loop here. The sum of the voltage rises must be equal to the sum of the voltage drops. There's 3 resistors, each with the same resistance, so I know that their voltage drops have to be equal to 2. So I have a +6, a -2, a -2, and a -2, all equals 0. So there's going to be a 2 volt drop there. Now on the outside, when that switch closes, I'm going to have a third loop, another independent loop. And I can easily see that the voltage drop across these will each be 3 volts. Now because I added a parallel branch, we know by heart now that REQ goes up and REQ goes down. REQ goes down and current goes up. REQ goes down and current goes up. So this is what gets us in trouble here, because the overall current in the circuit does go up, but does the current through A change? And the answer is no. So the answer, my long-winded way of saying you were all wrong, the current is going to remain the same. The overall current increased, but only increased to produce the new current going through this branch. So let's say that the current, let's say if each one of these resistors was 1 ohm, the equivalent resistance here would be 3 ohms, so 6 divided by 3 would be 2, so 2 amps would be my current going in initially. But when I close that switch, I'm going to have more current going through this branch. So the amount that the current increases by is just the amount needed to send current down this parallel branch. This voltage didn't change because nothing in that loop changed. And if voltage didn't change, current didn't change, so current in A remained the same. The current splits. So remember, the overall current from the battery is now going to increase, but the amount that it increases by is the new amount that's going to go in this branch over here. And that would need to be 3 amps. So the current initially leaving the battery was 2 amps. When the switch was open, the current leaving through the battery was 2 amps, and there was 2 amps of current going through resistor A. But then when the switch closed, overall resistance went down, overall current went up, and guess what the new current is coming out of the battery? It's 5 amps. Well, guess what? 2 amps still go down there, and now 3 amps go down there. So the current does split, but the overall current also increased. So the overall current increased by the amount that it needed in the new branch. Now the reason why a lot of us get into trouble with this kind of problem is because in class we've been doing a lot of this, where we had a circuit like that. And then maybe we had a switch there and a circuit like that. So when that switch closed, this bulb dimmed, or when the switch, when that switch closed, that bulb got brighter. And we justified that by saying, oh, well, we added another parallel branch, so overall resistance went down, overall current went up. But look, this resistor is in series with the battery. So whatever current is coming off the battery, that resistor is also going to get. Here, none of these were in series with the battery. They had their own loop with the battery. So they're directly connected to the voltage source. So adding another parallel branch isn't going to change anything about that guy right there, about that branch. And that's why in the mystery bulb lab, if you had something that was, if you had a circuit like this one right here, this bulb was really, really bright, and if it went out, nothing happened to those two. They didn't even change brightness. If these two went out, then nothing happened to this one. It didn't even change brightness because it's in a direct link, it's a direct connection in that loop, for that loop rule, with the voltage source. Okay? All right. The very last thing that we're going to go over is terminal voltage. You guys have been on here for quite a while, so I'm sorry that it's taking long, but I wanted to make it a thorough review. Number 8 on the quiz. What is the terminal voltage of the battery in the following diagram? So we had a battery connected to an internal battery resistor, connected to a standard resistor, connected to another standard resistor, and that was it. And then drawn around the battery and this resistor, they showed us those dotted lines. That means that this resistor is inside the battery. And they told us that R equals 0.5 ohms. Typically the resistance of the battery will be pretty low. They had our fancy E symbol there, which stands for EMF, electromotive force, is 24 volts. That's the maximum possible voltage that that battery can give when there's no current running through it. But guess what? There's going to be current running through it because we have a closed circuit. This is 3.5 ohms, and this is 2 ohms. So, step 1, just like I said at the beginning, we want to find Req for this circuit. I had somebody ask me today, does it matter if this resistor is technically inside of the battery? Does it change how I do my math? Absolutely not. That's why there's a dotted line there, because you can pretty much just ignore the fact that that's inside the battery. So the total equivalent resistance is just going to be the sum of all those because they're in parallel. So my equivalent resistance comes out to be 6 ohms. Step 2, find the total current of the circuit, which is going to be the voltage divided by the equivalent resistance. The voltage of the circuit is the 24 ohms, the 24 volts. It's been a long night. The 24 volts divided by the 6 ohms, which comes out to be 4 amps. Good. Okay, Ms. Zamzo, I got step 1 and step 2 down. I'm a pro at that. Now, how do I answer this question? What did they ask you for? They asked you for terminal voltage. And remember, the terminal voltage, this is A, and that's the internal resistance, and this is B. This is A, this is B. Trevor says, can you elaborate on step 1? Step 1 is to find the equivalent resistance of the circuit. So I'm going to treat this resistor as if it's in series with this one and this one, because it is. So really I just have 3 resistors in series, so all I have to do is add up their individual resistances. So the first resistor was 3.5, the second one was 2, and this third one here was 0.5. So just because this resistor is inside the battery, it doesn't change any of the math that we do. So my overall, did I add something wrong? 3, 4, 5, 5, 6, no, that's right. So my equivalent resistance is 6. And then to get the current running through this circuit, of course it's going to be the same all throughout the circuit. It'll be 6 amps anywhere in here. because it's series. So it's the same throughout. Sorry, we said 4, didn't we? My goodness. It would be 4. So we would have 4 amps there, 4 amps there, and guess what? We'd have 4 amps running through there as well, running through the battery. So the terminal voltage is if I took a voltmeter across section A and B. So here is where I'm going to put my leads. And there's my voltmeter there. What is the electrical potential difference from this side to this side? So that VAB is going to be equal to the EMF minus the current of the circuit times the internal resistor. So this E right here stands for EMF. That is the electromotive force. Now it's not really a force. Back when Galvani made dead frog legs move by using electricity, he thought it was the life force. It's before they knew what voltage was. But the term kind of stuck, so we call it the electromotive force. It's really the maximum possible voltage of just this guy right here without any current running through the battery. In this case, they told us that the EMF was 24 volts. We are looking for the terminal voltage, usually written with a subscript AB, because we can think of this as point A, this is point B, and that resistor technically is in the battery. So the voltage drop across the battery is going to be equal to the total voltage minus the current, which we found to be 4, times the internal resistance, which they gave us to be 0.5. So VAB is equal to 24 minus 2 volts. So 24 volts minus 2 volts equals 22 volts. So the voltage drop from here to here is 22 volts. The drop from here to here would get us all the way back to 24 volts and using the full loop. How does a battery drain? So if you think of a battery very simplistically as having, of course it's not actually right down the middle, it's usually a cylinder within a cylinder, but if you think of having all of these charges on one side and then giving them a reason to go to the other side, connecting away, these charges would rather be over here. So when a battery drains, all of the electrons have been moved, pretty much all of them have been moved to the other side. And now they're at a lower overall potential, and they're where they would rather be. So when the battery drains, there's no reason for these charges to go back the other way, even if the battery's connected, because they're at a state of lower potential. They're where they would rather be. We can force them to go back to the other side if it's a rechargeable battery by plugging it into the wall, adding electricity, and forcing them back to the other side. Alrighty. We have not talked about electrostatics at all. So I'm going to do the remaining 3 questions on the back of the quiz, because that'll be about the extent of our electrostatics. On the back of the quiz, it said that we had 2 static charges that are exerting a force F on each other when they're separated by a distance d. So I have 2 static charges. It could be whatever, some positives here, some negatives here, but whatever it is, the force between them, remember, it's going to be equal in magnitude and opposite in direction. The force between them is F. The distance between them, or technically between their centers, they told us was D. Now they want to know what the new force will be if the distance is tripled. So if I take these same charges, and now I triple the distance between them. Well, common sense should tell you that the magnitude of this force is going to go down because they're not as close to each other. And you know that whenever I have those bits of paper in that charged straw and I'm trying to pick up the paper, that the closer I get the straw to the paper, the larger or the stronger the force is on the paper. So force is going to definitely go down, but by exactly how much? Well, we have to look at our Coulomb's law equation, which is the electric force is equal to Coulomb's constant, which never changes, times Q1 times Q2 over R squared. R is just the distance between them. Q1 is the charge on sphere number 1, and Q2 is the charge on sphere number 2. Both of the magnitude of both of those charges determines the force between them. And of course, K stays the same. So in this question here, K remains the same, Q1 remains the same, and Q2 remain the same. They didn't say that we changed the charge on the objects, we just moved them further apart. So now I can write my proportionality. Force is proportional to 1 over R squared. It's not equal to 1 over R squared because I'm not factoring in these guys. So I'm not calculating in an exact force. What I'm calculating is a multiplication factor. How much did my force change by? So if my distance was doubled, then I need to plug in tripled. I need to plug in a 3 for my R. Well, 1 over 3 squared is equal to 1 over 9. So my multiplication factor is 1/9. So what I'm telling you is that the new force, which I'm going to call F prime, is equal to the old force times 1/9, which can also be rewritten as the new force is equal to the old force divided by 9. 1/9 of the old force is the new force. Yeah, it's a ratio. So thank you. This right here is giving me the ratio of the old force to the new force. Awesome. That is the first bonus question. The next one says that if we have 23 coulombs of charge pass through a lamp, in 5 seconds, calculate the current. So what do we want to find out? We want to find out current. What is 5 seconds? That is time. And what is 23 coulombs of charge? Well, that's Q. It can be written as lowercase or capital QI. Either way is fine. So what's the equation that relates current, charge, and time? Oh, well, current is the rate at which charges pass. So current is going to be equal to charge divided by time. Or I could say current is equal to charge divided by time. This equation is on your formula chart. Use your formula chart. All these equations are in one spot together. I know mechanics is kind of annoying because they kind of mix them all up. Sometimes it doesn't seem like they're grouped together, even though they are. The electricity magnetism questions get their own box on the formula chart, so definitely use this because you don't have to memorize these. You're taking the AP test without the formula chart? Wow, that's pretty impressive. But I guess if you're, 10th in the region for UL Science, you had to memorize those equations for that test. So I think you could do it. All right, what do we want to find? Charge? No, we want to find current. Look at me, silly old me. Why did I write a C there to find current? See, now you can tell I'm getting delirious. We want to find I for current. So I is equal to Q over T. So Q is 23 coulombs. T is 5 seconds. 23 divided by 5 is 4.6. And what is current measured in? You guys should know this. It is amps, which is just a coulomb per second. All right, that was the second one on the back of the bonus. And then the last one, this will be our last question for the night. We have a 30 microcoulomb charge. it is 16 centimeters away from a 20 microcoulomb charge. Calculate the force in newtons exerted on the 30 microcoulomb charge. So 30 microcoulombs, we'll just call that Q1. It does not matter if it's Q1 or Q2 because we're multiplying them together, so it really doesn't matter. This is going to be my distance, or my R value, and this is going to be my Q2. They want to know force. My equation is force equals KQ over R squared. So the only thing I'm missing is K. That's my constant, which is 9 times 10 to the 9th newtons meters squared per coulomb squared. So my force is going to be equal to 9 times 10 to the 9th. That's my K. Check. Times Q1. Q1 is 30 microcoulombs. Whenever you see any kind of prefix in front of the base unit, alarm bells should go off. You need to convert. Your brain should go convert, convert, convert. So 30 microcoulombs has to be converted to coulombs. On your formula chart, it tells you that micro has the symbol mu and the multiplication factor is 10 to the negative 6. That is on your formula chart. So literally all you have to do is go 30 times whatever that multiplication factor is, 10 to the negative 6, times Q2. Q2 is 20 microcoulombs. Alarm, alarm, alarm. Convert, convert, convert. Look at that. 20 times 10 to the negative 6 divided by R squared. Oh no, there's another convert there. I need to convert centimeters to meters. Divide by 100, 0.16 meters. So I'm going to put 0.16 down here, but do not forget to square it. Do not forget to square it. Do not forget to square it. That is the most common mistake on these force problems. What kind of force are we calculating? The electric force, which is much stronger than the gravitational force. And that came out to be 211 newtons. Bam. We're done. I don't even know if there's anybody left on here, but we're done. So if you have any last minute questions, maybe you can come in to see me before school tomorrow if you're A day. If you're B day, what's tomorrow? Tuesday? I should be there for a little bit after school tomorrow. So I'm going to go ahead and stop the recording. Stop screen sharing.